for number 8, this is kind of just bringing in a situation, and it's asking you to think about the context. Really not doing anything else. It's not really going to ask you a test or an interval or anything like that, but it is asking you to think about what's going on, and it's going to check to see if you understand the situation. And so we're going to look at letter A, number 8. It says, what sampling design was the magazine planning to use? What do you think? And why? Why do you say stratified? Right, 2 groups, and they sampled a portion of those from each one, right? They took 450 owners from the American and 450 from the Japanese models. Obviously, there's a lot more people than that. Now, if we think about this, who's the big population in this case? Who are they really asking? Like, where are these people coming from? It's the people that read the magazine, right? It's the magazine owners. Now, this is some sort of consumer magazine. We don't know who it is. We don't know anything, but we know that from their members, from their subscribers, this is the question, like, if you own a Japanese, or it probably asked you 2 questions. They asked you what kind of car you drove, and they asked if you had to buy another car, would you rebuy that same make or model or whatever type it is again. And so you have 2 groups. You sampled from part of them, and so that makes it stratified. What about the next question, part B? Part B says, what difference do you expect to see in their polls? Why 2%? Exactly. They told us here in the bottom that, no, we don't know the real truth, but they're like, let's just suppose we do. Let's suppose that 76% of all owners that have American cars would buy another American car. 78% of all Japanese car owners would buy another Japanese car, right? And so you've got this kind of scenario where I know what the parameter is, right? And so if I take samples from that, we've learned from chapter 18 on that if I take a population, a sampling population, a sampling distribution, and I sample from that, my center, my mean is going to be exactly the same as my sample. So when I take from the American owners and I take from the Japanese owners, if I sample them, I haven't done that yet. But if I had, right, and if I have the numbers for those samples, then I would expect those statistics to be exactly the same as the parameters, right? So we would think that. Now, we know that the 450 people, we don't know how many of those people would actually go back and buy their cars again. But we do know that of all American owners, the 76% and 78% of Japanese cars. So that's where you're going to get the 2% from. No extra calculations or anything like that. Okay, part C. What kind of standard deviation do you expect to see here? Well, this is our pretty big formula. Now, this is located in your formula sheet. So if you haven't checked that out, I would take a minute. I would grab that formula sheet out, go to that part with the tables, and find where it says 2 proportions, sampling error, or statistical, I guess it's called sampling distributions. You have statistics, the standard deviation of the statistics, things like that. Make sure that you can identify those. It looks like this. You've got P, Q over N, actually P1 and Q1 over N1 plus P2, Q2 over N2. This is essentially my sampling distribution's standard deviation, which really we call standard error, right? Because it's the standard deviation of just the statistic, not the overall parameter. And so, okay, and so if I plug all this information in, it would look something like this, right? So we're going to use, I'm just going to kind of go in the order they used in the book. 0.76 times 0.24 divided by 450. Okay, plus 0.78 times 0.22 divided by 450. Now we don't know p hat. Like if they had actually done the sample, we really, if we know the parameter, like 0.76 and 0.8 and 78, we would always use those. In a scenario where I'm doing a confidence interval, I won't know those numbers. So we use that estimated value as p hat. If you have the newer version of the formula sheet and not taken one of mine from class, then you should have two versions of that formula, and you'll see the differences there. It's the same formula, just one's using statistics, the other's using parameters. In this case, we're going to end up with 0.028 as the standard deviation. Part D is asking us, it says, of course, or D says, sketch a sampling model for the difference in the population proportions. We know that it's going to be approximately normal, the sampling distribution. So it looks something like this. All right, we're going to have the center at 0.02. I'm going to write these all in decimals. Right, so if you kind of look at it this way, it's going to end up going, I'm going to write these as decimal points. So 0.048. This is going to be 0.074. And this is going to be 0.102. Okay, so that's that one right there. If you go down the other side, you're going to have negative 0.8 and then negative 0.8? Nope, sorry. Got to write the decimals. Negative 0.008. Is it? Yep. This is going to be negative 0.036 and then negative 0.064. Out one standard deviation is 64. You got 2, it's going to be 95. You're going out 3, it's going to be 99.7%. Now, all of that said, this kind of leads us to the bottom question. Part E. Could the magazine be misled by the poll? Okay, concluding that the owners of American cars are happier with their vehicles than Japanese cars. Is that something that they would think is going to happen? And then really, why or why not? Is it probable that the magazine could be misled by this poll? We don't know the results of the poll yet. Judging by the distribution, do you think it is possible, probable, that basing it on the results and the likelihood of what those results could show, do you think it's possible for me to get contradictory results if I did lots of these samples? Why do you say yes?
Because the zero is going to stand.
Where's
one, sorry.
0 falls right there. That's a problem. It is within 1 standard deviation of the mean. Okay? Super close. Meaning that some samples will most likely generate a negative difference. Some samples could definitely generate a 0 difference. Some samples could also generate, most of them, will generate a positive difference like it should. Most of them will generate around a 2% difference. But it is likely, more than 16% likely, that I'm going to get a negative difference. Do we understand how that's possible? The negative differences fall right here, right? There's 0 somewhere in this area. And so if I were to get a sample, and what's the probability that the difference could be 0? I could use normal CDF right now, negative infinity, up to 0, using the mean of 0.02 and the standard deviation of 0.028, and we could work out that probability. I don't need to, though. That is way overkill. Is 0 an unlikely result as a mean? No. It's really going to be a pretty common result. Is it unlikely to be negative? No. It's likely to be negative. Probably not as likely as it is to be positive, but it's going to happen from time to time. More often than I would. Point is, because 0 falls within one standard deviation of the mean, it is possible for this magazine to be misled by the poll. That's how you should answer that question. One of the key elements here that you have to understand is that when we're dealing with these differences, we are doing the percent of Japanese owners minus the percent of American owners, right? That's the, we'll call that the percent, the difference. I did it this way because the book wrote it first Japanese, and then America was the large one, right? We said 0.78 minus 0.76. That's where we get our 0.02. That's where we get our 2%. Is it possible somehow that this number could be greater? Yeah, if we happen to get 79% American and 78% Japanese, then you would end up having a negative difference, right? 78 minus 79 is negative 1. So you would just say, oh, well, if it's a negative difference, that would mean that percent more for Americans versus the Japanese owners. Does that make sense? Understanding the differences, how you write this out, makes a big difference, right? I said Japanese minus American. That's how we got our mean here. We said 78 minus 76. That's where this number comes from. So every other time when I'm talking about a difference, I'm going to subtract it, the Japanese percent minus the American percent. That has to happen this way. And that's what we're looking for here. If I get 0, it means these two numbers have to be the exact same number. But if I get a negative difference, the blue shaded area is, that would mean that this second number, the American percentage, happened to be the larger number in the difference of the two groups. That would mean that the American group is larger than the Japanese group. That would be a false statement. That would mislead the company because they would write a report out saying, our poll showed that the American owners are more likely to buy cars than their Japanese counterparts. Right? When in fact, the opposite was true, and they would have misled their readers even though the data was collected legitimately. It's just too close for it to be consistently always the right way. Number 18 is kind of setting you up, kind of as a step-by-step guide to doing a two-sample significance test, right? In future questions, I think question 20, beyond that, question 20, you get into somewhere. It just says, provide statistical evidence. And it's like, well, what am I supposed to do? Whatever you'd like. Well, whatever's appropriate is probably more relevant. Some things are appropriate. Sometimes you totally get a choice. In this case, it's definitely a test. It's talking about hypotheses and things. Let's just kind of start with part A. In this study, they identified 450 people with cardiac disease. They evaluated them for depression, and then they followed up after 4 years. Out of the 361 patients with no depression, 67 had died. Of the 89 patients with depression, 26 had died. Among those who suffer from cardiac disease. Now, why would I state that? Why is that a relevant statement right now? Because that is the exact population of interest. Which means that when I get done with this whole study and I go talk about the results, this only applies to cardiac patients. People that have had cardiac disease. It doesn't apply to anyone else. Because the population had to have a certain requirement, and then that was it. Okay? Among those who suffer from cardiac disease, are the depressed patients more likely to die than non-depressed patients? That right there is P. Okay? One of the reasons I don't normally grade that is because literally written for you in the question, if I don't know this, if I don't understand this, I really don't know where I'm kind of going with the rest of the test, right? So it's usually pretty obvious, right? In this case, they want to know what kind of study was done, what kind of design was used to collect this data. Notice the question. Remember last time they asked this? They said, what sampling technique was used? Notice they didn't say that this time. They said, what design? What is designs? Experiments and what is not an experiment? An observational study. Chapters 12 and 13 will consistently pop up in these styles of questions, right? Samples, sampling techniques, experimental design, observational studies, all of those things kind of play a part in this because they have little key factors that need to be considered. In this case, we have an observational study. No treatment was done, no manipulation was done, they simply observed what happened naturally. Part B, how do we write our null and alternative hypotheses? Let's go ahead and agree on something, right? So P, we said that's right there. Phantom for H, O. Let's go ahead and use D and ND for depressed and non-depressed because that's the terminology they were using. And that clearly defines my two parameters, right? So HO would be, what about the depressed is what compared to the percentage of not depressed patients? What? Equal to, that's right. This is the null hypothesis. You do not get to choose. It is always the first proportion is equal to the second proportion 100% of the time. If you ever forget this, open up your calculator. If you'll go to the 2 prop Z test, you don't even have a space for the null hypothesis anymore because it automatically knows what that's supposed to be. The question is, are these two percentages equal to each other? Right? If we keep going, what's the alternative going to look like? We want to know, is the percentage of people that have depression, is that greater than the percentage of people that do not have depression? When you're writing out your null and your alternative hypotheses, this would be a minimum requirement. HO, colon, P with a subscript that is defined, equals, and the same thing on the other side. Alternatively, I have to have HA, colon, and the same thing. I have to have that alternative, that sign kind of connected to what we're reading in the paragraph, right? This is right here. Are the depressed patients more likely? That right there, that one phrase is exactly where we discover what alternative to use because that is what they're trying to show. Okay? A little bit on the side here, there are other ways to write out our null and alternative in this situation. We could write the differences, and you'll see this from time to time. I typically write mine out the way you see here, but I want to make sure that you understand that this is the same exact statement as you see on the other side. I'm just really subtracting the two differences from one side to the other. It's just like a little mini equation. Those two things are the same. You do not have to write both of these. In fact, please don't. It's a waste of your time. Just pick one. I usually write this way, but both of these ways are good. From whatever you're going to put in your null and alternatives, they have to match. Don't kind of mix and match them, right? Pick these two or pick these two. Any questions? No. Okay. A, our assumptions and conditions. We're kind of running short on time here, so we're just going to kind of run through these. Do we have a random sample? No. They did not say anything about it being random. In fact, an observational study or an experiment doesn't usually have or expect to have random samples, right? You randomly assign treatments. In this case, we don't have an experiment, right? So we say no, but representative. We believe that this sample is representative of any patients who have cardiac disease. We don't have reason to think it's different. Independence, this is kind of not even necessary because it's pretty obvious. Death is independent. This, on the other hand, is not obvious. Independent groups. Do you think the group of patients who have cardiac disease with and have depression would influence, in terms of like death, the people who don't deal with depression. You say, no, these are probably random people. They probably don't even know each other. And so groups are independent. Be careful, that's not always true. Now, in terms of how do we deal with a non-independent group, for right now, that's a big problem to have, right? In quantitative data, totally different ballgame. If it fails, we know how to deal with it. If it fails here, we really aren't going to talk about that. All right, next part. We have random independence. We have 10%. In this example, we have two sample sizes. We have 361 and 81. These are both less than 10% of all patients that have cardiac disease, right? No big deal. That's pretty obvious. That's probably in the millions of people, so that works out well. 10%. Remember, notice I did both samples there, both sample sizes. 10%, so we have success and failure left. In this example, we had 89, and the other one was, let's see, 294. And then the other one, we had 63 and 26. All greater than 10, right? So we're good on success and failure. A lot of students have yet to do this. And some students, I've never seen you check your assumptions and your conditions, ever. We've been doing this for 4 weeks now, at minimum, probably more like 5. Make sure you do this. This is easy points. It's a little tedious, but it's gonna give you points, right? PHAN, name the test. This is a 2 prop Z test. That's an easy one. PHANT, we need to get our test statistic, our p-value, and then we'll make a conclusion. Now, I'm reading out of the key, so my percentages, my decimals would be slightly off from yours. Yours is probably a slight bit more accurate. So in this case, we had a z-score of negative 2.22 and a p-value equal to 0.0131. To write out my conclusion, how would we do this? All right, so let me back up a minute. If you look at my question here, we've gotten down through, we've done A, B, C, and we're about to finish up D. What would my conclusion of this be? Do we reject or fail to reject? Let's decide to use an alpha level that's a standard size, 0.05. What would we do? What would we decide to do here? I reject my null. Okay, because my p-value is less than my alpha. All right, I got two things done. I rejected, and I made sure to reference the fact that my p-value was lower than the alpha level. That's why I rejected it, but I haven't put it in context yet. Let's kind of do that right now. How would I write out my conclusion here? Our evidence suggests what? Say that again? That the proportion of cardiac patients with depression I suggest that the proportion of patients Now, I focus on the disease, the people with the cardiac disease and depression that is greater than those without depression. If you said less, you could have said the people without depression would have had a lower percentage than the people with depression. Whichever way you're going to say it, you need to make sure that you say it the right way. I reject my null because my p-value is less than my alpha level. Our evidence suggests that the proportion of patients with cardiac disease and depression who, I guess they said, that die, the death rate is greater than those without depression. I kind of skipped that part of it.